Welcome back. In this session, we're going to talk about isotopes. Now, there's very little in this that you have to be able to do, so you just need to be able to give me the definition for what an isotope is for 6 marks. So we're looking at 2 bullet points, and then you need to be able to count subatomic particles and link it back to the definition to explain why 2 isotopes are isotopes. So for example, what I mean by that is why carbon-12 and carbon-13 are isotopes of carbon. And you just need to be able to count their subatomic particles, which are protons, electrons, and neutrons. Right, so if we look at our iPad, so your definition for what an isotope is they are atoms of the same element. Now I'm going to highlight what's important here. So atoms of the same element, they have the same atomic number due to the same number of protons. Now that's really important because they are atoms of the same element, which means they have to have the same atomic number. If the number of protons in the nucleus is different, well then you are dealing with different elements. And we'll talk about that in a second down at the bottom of the screen. So same atomic number means they have to have the same number of protons because that's what the atomic number is. It's the number of protons in the nucleus. So if you were looking at all of the isotopes of carbon, they all have to have the same atomic number or same number of protons. That's 3 marks. Next, they have a different mass number due to a different number of neutrons in the nucleus. The mass number of an element is the number of protons plus neutrons in the nucleus. Now we've just said for isotopes of the same element, the protons have to be the same. So that means if they are isotopes of the same element, the only subatomic particle that can be different is the number of neutrons in the nucleus. So what makes something an isotope? Same atomic number, different mass number. Same number of protons, different number of neutrons. Now underneath my definition box, I have each element has a unique number of protons in the nucleus. So carbon is a different element to nitrogen, which is a different element to oxygen. Now, from the information given at the bottom of the screen, carbon's atomic number is 6. Apologies. Carbon's atomic number is 6. Nitrogen's atomic number is 7, and oxygen's atomic number is 8. That means carbon is going to have 6 protons in the nucleus, and it is the only element that has 6 protons in the nucleus. Nitrogen has 7 protons in the nucleus, and it is the only element with 7 protons in the nucleus. So when you are comparing atoms, if you find out the number of protons in the nucleus, that will let you identify what the element is. And each element has its own unique number of protons in the nucleus. Now next up is we're going to talk about the specific isotopes and comparing them in terms of their formulas and their names basically. So in nature, each element is made up of a mixture of isotopes. We'll come back to this idea in the next lesson when we talk about the relative atomic mass. So the specific example we're going to look at is nitrogen. Nitrogen in nature has 3 stable isotopes: nitrogen-14, nitrogen-15, and nitrogen-16. Now, when we look at the name, when it spells out the name of the element first, that's always going to be the name of the element, so nitrogen. But the number that comes after the name, 14, 15, and 16, they are the mass numbers of the specific isotopes. So for nitrogen-14, the isotope has a mass of 14. For nitrogen-15, the mass of the isotope is 15, etc. Now, what's not given in a formula like that is the atomic number, but you don't need it because we're all super intelligent. We can find the atomic number from your periodic table, which is your formula and tables book, page 79. On the right-hand side of the screen, I've given you the little tile from your periodic table. So you see on the top, the atomic number of nitrogen is 7. So each of those 3 isotopes of nitrogen, they all have to have the same atomic number. How do I know? Because they all have the same name. So if we look at the name of each of them, nitrogen, nitrogen, and nitrogen. Because they are all nitrogen, they all have to have the same atomic number. They can't have different atomic numbers. Now, there's another way to represent the formula of an isotope, and it's called the nuclear formula. Now, I'll show it on the next slide in relation to hydrogen isotopes, but I am going to introduce it here just to get us used to it. Now, for our isotopes for nitrogen, now, when you were writing the nuclear formula, you write the symbol for the element first. So N is for nitrogen. Then on the top left, you write the mass number, which is this number there. It's the 14 for the first isotope. Then when you're writing the atomic number, it goes on the bottom left. So nitrogen has an atomic number of 7. The next isotope that we're going to be dealing with is nitrogen 15. So again, it has to have the symbol N because it's still nitrogen, but now the mass number is 15, but the atomic number is still 7. Then on the other side, we have nitrogen 16, and again, it still has the atomic number of 7. So when you are dealing with isotopes of an element, the only thing that's going to be different is this number here. It's the mass number of your element or your isotope. Now, in the next slide, we're going to talk about hydrogen. Now, hydrogen also has 3 stable isotopes. Now, the number 3 is common here because carbon, hydrogen, and nitrogen, they all have 3 stable isotopes. But not all elements do. Some of them have fewer, like neon has 2, or some of them have more. I think silicon has 5 or something like that. You don't need to remember that. You don't need to remember the specific isotopes of nitrogen and hydrogen. The only element where you need to be able to list off the isotopes of that element is actually carbon. And that will come up a little bit later in relation to carbon dating when you get to it in the radioactivity topic. Right, so hydrogen has 3 stable isotopes. They are hydrogen 1, hydrogen 2, and hydrogen 3. So they're the mass numbers of the isotope. And if you look at the diagram underneath, I've represented the number of protons in the nucleus with an orange circle with a positive charge because protons are positive. And I've represented the number of neutrons with a green 0 because they're neutral. Now, from your first isotope, this isotope is hydrogen 1. That's the one on the left-hand side. So it has an atomic number of 1. How do I know? Because it's hydrogen. When you look at the periodic table, that gives you the atomic number, even though it's not given in the formula yet. So it has 1 proton in the nucleus. Now, if you look at all 3 of those isotopes, they all only have 1 orange proton in the nucleus because they're all hydrogen. Next, if we look at hydrogen 2, which is the Bohr diagram in the middle, you'll see that it has 1 orange circle, 1 proton, but it also has a green circle that the other one doesn't have. And that is the number of neutrons. Now, when you're working out the number of neutrons of an element, it is always found by subtracting the mass number and the atomic number. So your atomic number is the number of protons in the nucleus, which is this number here. So it's always going to be 1 for hydrogen. But the mass number, that's these numbers over here. So we have 1, 2, and 3. For the first isotope, the mass number is 1, the atomic number is 1. 1 minus 1 is 0. And you can see that on the diagram on the left-hand side, there's no green neutrons in the nucleus. The one in the middle, that will be 2 minus the atomic number, which gives me 1 neutron. So 1 green circle in the middle. The third one, that would be 3, mass number of 3, minus 1, which gives me 2 neutrons in the nucleus. And that's why we see 2 green circles in the nucleus of the third one, the one on the right. Now, the purpose of that diagram is just to represent with a diagram how the isotopes of hydrogen are different. Same number of protons, different number of neutrons in the nucleus. And underneath, I've also labeled where the mass number and where the atomic number on the nuclear formula is. Mass number is on the top, the atomic number on the bottom. Now, where you might get a little bit confused with that is when you look at the periodic table, it's always printed, for Leaving Cert anyway, with the atomic number on the top and the mass number on the bottom. But for the nuclear formula, they're flipped the other way around. Now, my worked example that I want to have a look at is going to go through counting the number of subatomic particles in an isotope. Now, this specific worked example is in the notes for a reason because it came up, or something very similar came up in 2021, and very, very few students got marks here because they didn't read the question properly. So let's have a look. Carbon has 3 isotopes. So I'm going to highlight them as I go in different colors. So I have carbon 12, and I gave the full formula, but I also gave the nuclear formula as well. Now, for some reason, it's not saving my lovely highlighter colors. Then we have carbon 13. And then my next one, let's try green, is carbon 14. So there's the 3 isotopes of carbon, carbon 12, 13, and 14. Now, this next bit is the bit that everybody missed, and it's where people dropped huge marks. By referring to subatomic particles. That means in your answer, you need to count the subatomic particles for each isotope, but it doesn't mention which subatomic particles. You have to count all of them. So the protons, the electrons, and the neutrons. The one that everybody forgot was the electrons, and they didn't get any marks if they didn't talk about the electrons. Explain why these are all isotopes of carbon. So let's go to my pen. Draw a table and count. Now, for this one, I recommend that you draw a table here. Don't try to put this in a sentence, because if you try and phrase it in a sentence, you're going to forget something along the way. So we want to show that we've counted all of the subatomic particles for all 3 isotopes. The easiest and shortest way to do that is a table. So the first isotope we have is carbon 12. Now, carbon 12, the atomic number is 6, so the protons has to be 6. And the electrons will be 6. They have the same number of each. Then on the far side for the neutrons, to work out your number of neutrons, it is the mass number, which is 12, minus the atomic number, which is 6. That means there's 6 neutrons in the nucleus. For the next one, for carbon 13, it's still carbon, so 6 protons, 6 electrons. But now it's 13 minus 6 because the mass number of this isotope is 13. That gives me 7 neutrons in the nucleus. And then my last one, carbon 14, has an atomic number of 6. So 6 protons, 6 electrons. But now my mass number is 14 minus 6 to give me 8 neutrons in the nucleus. So same number of protons and electrons for all 3 isotopes, but different numbers of neutrons. That is going to be my first 3 marks in this question. Next. The next part, what you have to do is you have to link what you have just done to the definition which we learned off before. So here, link the subatomic particles to the definition. So if something is an isotope, isotopes are atoms of the same element, so same number of protons, but they have a different number of neutrons in the nucleus, which gives them a different mass number. So I'm going to phrase that as carbon 12, carbon 13, and carbon 14 all have 6 protons in the nucleus. i.e., they have the same atomic number. That's going to get me 3 marks. Now you'll notice I didn't mention the electrons there because the electrons don't have anything to do with the atomic number. The atomic number is just the number of protons in the nucleus, but you still had to show you counting them in the previous part. Now the second one is to tell me what's different. So carbon 12 has 6 neutrons. Carbon 13 has 7 neutrons. And carbon 14 has 8 neutrons. So they have a different number of neutrons or a different mass number, either or. And that's going to get me my 3 marks. Now, a question like this can be a bit sneaky, so take your time with it, draw a table, and then link it back into the definition. Now, the next page, we're just going to count the subatomic particles for some isotopes. Now, before we go into this, I am going to put a bit of a disclaimer on this. Whenever students have to count subatomic particles, genuinely, hands on heart, it is one of the worst answered questions on the entire paper, bar none. So forget about all of the difficult calculations. This is worse because people assume that they can do it, but then they forget something. So now, if we go down through it, the atomic number for my first isotope is given on the bottom left. So it's chlorine 17, so we fill it in. 17 for the atomic number. Now the mass number is the one on the top, which is 35. Protons comes from the atomic number, so I've got 17 protons and 17 electrons. For my neutrons, it will be the mass number minus the atomic number. 35 minus 17, which is 18. Next, for the next isotope of chlorine, the atomic number is still 17 because it's still chlorine, but now look, the mass number is different. It's 37. 17 protons, 17 electrons, and my neutrons will be 37 minus 17, which is 20. Now, here we go. Not too taxing even for me. I never do maths in my head. So we're doing well that I haven't made a mistake yet. Now we're going down to neon. Neon has two stable isotopes. So the atomic number is different because the element is different. The atomic number is 10, the number on the bottom left. The mass number is 20. So 10 protons, 10 electrons, and now look, 20 minus 10 is 10. So 10 neutrons as well for that one. But then we have neon 22. It has 10 as the atomic number, but 22 as the mass number. 10 protons, 10 electrons, and 12 neutrons. 22 minus 10 gives me 12. Now, I'm not going to go through any more than that, so there's quite a few of them for you to practice in the notes, but it is really important that you don't skip over this. When we start talking about the relative atomic mass in the next class, we will actually be referencing subatomic particles again. So it's a really key skill that you have to be able to do, and please don't skip it because it's going to cost you big if isotopes come up. Now, on the next page, I just have a picture of a periodic table. That's actually for the next one, for my next question. By referring to subatomic particles, explain why oxygen 16, 17, and 18 are considered isotopes of oxygen. Now here, as soon as you see this phrase, by referring to subatomic particles, alarm bells should start ringing straight away because that is what I would call a trap question. Draw yourself a small table. It doesn't have to be drawn with lines. I don't care. As long as you can lay out that you have protons, electrons, and neutrons and you're counting them, it's absolutely fine. If you would rather do it as a sentence, that's fine. It's just a little bit more work, so just make sure you're getting all of the information. Apologies. So I have oxygen 16, oxygen 17, and oxygen 18. Now, when the formula of the isotope is given like that, when the identity of the isotope is written as oxygen 16 and oxygen 17, what it doesn't give you is the atomic number. However, you're all super intelligent. You can find your atomic number by going back the way to the periodic table here. And oxygen is found here. So your atomic number is that number on the top, it's 8. So now I can fill out the rest of my formula. The number on the bottom for each of these nuclear formula is 8. Then I'm going to make a list: protons, electrons, and neutrons. Now I'm just going to change color of my pen to green while I fill this in. Now, protons, that comes from this number down here, your atomic number. So they will all have 8 protons and they will all have 8 electrons. Then underneath, to work out your neutrons, you do 16 minus 8 is 8, 17 minus 8, which is 9, and 18 minus 8, which is 10. So your 3 isotopes have the same number of protons and electrons, but different numbers of neutrons. Now we need to use that and link it to the definition. So my next point is to say oxygen 16, oxygen 17, and oxygen 18 all have 8 protons in the nucleus. i.e., they have the same atomic number. But oxygen 16 has 8 neutrons. Oxygen 17 has 9 neutrons. And oxygen 18 has 10 neutrons. Now, we want to extend that a little bit, link it to your definition, i.e., they have different mass numbers due to different numbers of neutrons. Three for counting your protons, 3 for saying they have the same number of protons, and 3 for showing that they have a different number of neutrons and linking it to the definition. Now, a question like that is quite a tricky, dangerous one, so please, 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 number 1, use a table. Number 2, link it to your definition and you'll be fine. The 2 bullet points in the definition. Now, before we move on, just one thing I want to note here is, because we've seen it come up a little bit. So oxygen 16, 17 and 18. When it looks like you have 3 isotopes of an element, it doesn't necessarily mean that the number of neutrons differs by 1. An example of that would be neon 20 and neon 22. They actually differ by 2. There's no neon 21, or not a stable isotope anyway. So just be careful. When you see 3 isotopes of an element and you've worked out the number of neutrons for one, don't just add 1 neutron for the second and another neutron for the third. Actually calculate it by taking the atomic number away from the mass number, just in case it has skipped over an isotope if it's not stable, for example. Okay, that's it for isotopes. Now, hopefully you've picked up something useful there and now can figure out how to show what by referring to subatomic particles questions mean.